Welcome to this presentation of our paper, Multi-Agent Path Planning in Complex Environments using Gaussian Belief Propagation with Global Pathfinding. This work addresses the challenge of highly dynamic multi-agent path planning both on a global and a local level. By leveraging factor graphs, one for each robot, and Gaussian belief propagation for message passing, the factor graphs contain 4 different dynamic constraints. We contribute 2 approaches. The first approach is called waypoint tracking. This is where a global planner computes the path from A to B, accounting for the static environmental obstacles. The waypoints found by the global planner are simply used by the local planner, which is the factor graph and Gaussian belief propagation step, to follow. Now, the other approach is the path tracking approach. In this approach, a new factor has been introduced into the Gaussian belief propagation, the factor graph, which we call a tracking factor. This tracking factor measures the continuous path between waypoints received from the global planner, and it pulls the factor graph for each robot towards this continuous path. This way, the robots are able to adhere closer to the path that they've been instructed to follow. The tracking factor pulling force is visualized by the red line on the clip to the right, where on the left-hand side you can see how without a tracking factor it produces a lot more of a chaotic movement pattern. Now, the collaborative approach uses both RT star and a structured planner, where the sample-based method is able to achieve a 14% decrease in the perpendicular error, but with a lot more inter-robot collisions. However, when using the structured planner, we're able to achieve a 16% decrease in the perpendicular path deviation error, and we're able to maintain 0 collisions at all, which is highly valuable, especially with the path tracking approach. We do see that these results deteriorate with higher failure probability of communication. However, the path tracking approach does not fail spectacularly compared to the waypoint tracking approach, maintaining a slight offset in total collisions and a better perpendicular path deviation, even with high failure probabilities, which also speaks to its stability. This work also contributes a robust simulation framework, Multi-Agent Gaussian Inference Collaborative Simulator, or MAGICS for short. This framework makes it easy to declaratively construct your environment, your robot spawning parameters, and the simulation parameters. Furthermore, the interactive user interface provides a bunch of functionality so that you're able to switch scenarios, simulation settings, live on the fly, and you're able to adjust all of your parameters, along with a bunch of visualization tools.